Good afternoon, everyone. I hope you can hear me. For those of you who don't know me, my name's Steve Miller, and I'm currently the Geophysics Vice President, or one of the Geophysics Vice Presidents of the Royal Astronomical Society. And I'm chairing this meeting because neither our President nor our Vice President-elect is available today. So this meeting is taking place via a webinar. If you look at the top left of your screen, you should see a small green shield. And that will tell you that you're using the most up-to-date version of Zoom and that it is secure. The meeting is being recorded. You should all have been given a notice of that. Questions at the end of the lecture, which I'll be introducing shortly, can be submitted via the chat facility found at the bottom of your screen. Your questions will only go to the panelists and they will then be read out by Council Member Dr. Belinda Wilkes. But I've got to make a few announcements first. So firstly, the annual general meeting of the Royal Astronomical Society will take place at 1600 hours, 4 o'clock on Friday, May the 13th, 2022. NAM 2022 will be held at the University of Warwick from Monday the 11th of July to Friday the 17th of July 2022, and we're expecting conference registration to open very shortly. Voting in RAS Council elections is now open. It will close at midday on May the 12th and is this year in electronic form only. So you will need to have voted by midday on the 12th of May. We have also opened nominations for RAS medals and prizes to be awarded in January 2023. The deadline for nominations is July the 31st, with the exception of the Education Awards and the Annie Maundham Medal for Outreach, which have a deadline of Friday, 30th of September. And a reminder, there is still time to nominate the Patricia Tompkins Undergraduate Prize. The deadline is 31st of May. Please visit the RAS website for more information. And finally, the deadline for the Caroline Herschel Prize Lectureship is the 30th of April. Please visit the William Herschel Society website to complete an online application. So now I'd like to move on to the main business of today's meeting. Today we have Dr. Sana Kotar of the University of Cambridge. She will be delivering the Harold Jeffries lecture for this year. After studying geophysics at Utrecht University, Sana completed her PhD at the University of Berkeley, California in 2013 on heterogeneity and flow in the deep earth. She then became a postdoctoral researcher at the University of Cambridge in the UK, funded by a Draper's Company Research Fellowship from Pembroke College. In 2015, she became an assistant professor at the University of Cambridge in global seismology. Currently, Sana holds an ERC starting grant to zoom into and understand the Earth's major internal boundary, the core mantle boundary. So Sana, over to you.
Thank you for that introduction, Steve. And yeah, it's a great pleasure and honor to be giving the Jeffries lecture to you today. So I will indeed be taking you on a tour to the core mantle boundary, almost 3,000 kilometers deep inside the Earth, almost halfway to the center of the Earth as well, to show you the research that my research team and I are doing on that boundary, kind of mapping and revealing the kind of secrets that are hidden here within the deep mantle. And so here's a little cartoon of the core mantle boundary. So this boundary Beneath this boundary is our iron liquid outer core, which is very vigorously convecting, and it creates our magnetic field, allows us to have life on our planet. And above the boundary is the solid silicate mantle, which moves very, very sluggishly. It's only changing over geological timescales. But the convection here is, the dynamics here is part of the dynamics of our plate tectonics, and it is forming the surface of the planet as we know it today. So the heat flux across the core mantle boundary plays a really big role in driving the dynamics on either side of this boundary, and then plays a big role in the thermal history of our planet. As well, there could be some sort of material flux across the boundary as well. On the core side, the very vigorously convecting liquid, we cannot really map or see these variations using seismic waves because the density variations are very, very weak. On the mantle side, though, seismic waves uncover a whole host of heterogeneities. And here's a bit of a cartoon showing what sort of landscape might exist there, or an interpretation of processes that are happening on that side of the boundary. And so I will be showing you some evidence of this in this talk, and showing you the approaches that my group take to uncover this. These are images made by seismic tomography. So seismic tomography is reasonably similar to medical tomography. We pick up loads of waves, earthquake waves around the planet, and we check if those waves are arriving sooner or later than we might expect. And by using many of these wave or travel time arrivals, we can make a map of where in the mantle the material is being slow or being fast. And we plot these typically red to blue maps like is seen here. So these are maps of the structure observed just above the core mantle boundary. And this is by 5 different studies. And so there's differences between these, but there are some large scale similarities between them as well. So overall, the variation in this map is roughly 5% in wave speed velocity. And where it's red, it is slower than the surroundings. And the simple interpretation is that the material there is hot and is probably going up. And where it's blue, the material is fast, and we interpret that as being cold, or the material going down. And so one of the common features within these models is that there is these large red blobs beneath the Pacific and one beneath Africa. And this is repeated in all the different models. And it is surrounded by these broad blue anomalies. And those are interpreted to be tectonic plates that have subducted down into the mantle and are kind of collected on the core mantle boundary as this slab graveyard. The slow areas are a bit of a mystery as to what they are, though. So in the community, they have been dubbed large low shear velocity provinces, or LLSVPs, or a bit shorter LLVP, but it is still very much a bit of a mouthful, this acronym. I'm not sure we do great on naming it. I think astronomers have done really well naming a black hole, because everyone has heard of a black hole, if you know what it is or not. But very few people will have heard about a large low velocity provinces, even though these are quite big mysterious features that we have sitting within our mantle. And so these anomalies are about 3 to 5% slower than the surrounding material. And they are mainly located in these 2 big blobs beneath the Pacific and Africa. And they also appear to be kind of located at the equator, and they are dominantly beneath these areas where we see hotspot volcanism, or we see these mantle plumes coming up that feed this volcanism and create a lot of the islands in the Pacific, as well as around Africa and Iceland, and also feeds into the East African rift that is breaking up the continent there. So they appear to play some major role in the overall mantle dynamics. As you just saw in these tomographic models, they appear quite blurry. In this cartoon representation, I've kind of depicted them as piles. Because when we do look with higher frequency waves, we do observe that the boundaries of these anomalies, it should be reasonably sharp. But yeah, these anomalies are thousands of kilometers across and are in places hundreds of kilometers thick, maybe in some places up to 1,000 kilometers high. So quite big features. When we zoom in closer to the core mantle boundary, we see this other feature, which we've also given an acronym to. It's called ultra low velocity zones, or ULVZs. And these are the anomalies that I'll mainly be focusing my talk on. These anomalies are only tens of kilometers high, so roughly on the order of the crustal thickness beneath your feet. And they are not seen in these tomographic images. And partly that is because the tomographic images are used with lower frequency waves than can observe these thin layers. And that is just due to computational limitations. And also, as I was showing in this talk, we really uncover these sorts of anomalies by looking at deformation of the waveforms or strange waveform phenomena. And it's hard to incorporate that into these tomographic models. These anomalies, though, are very, very extremely different. So they're at least 10% slower than surroundings, but probably even 30 or 40% slower than the surrounding material. And so they are very likely have to be some sort of anomalous compositional component. One obvious one would be that they are enriched in iron, and then they could be some sort of anomaly that has been a blob that has been there over the whole history of the planet, or potentially it's some sort of seepage of material from the outer core causing this iron enrichment being there. And some people have also speculated that they're not fully solid and they are partially melting on the core mantle boundary. So here's kind of a compilation of a couple of years ago of all the studies that have observed some evidence of an ultra low velocity zone or an heterogeneity on the core mantle boundary. These the pinkish background here is showing these outlines of the LLSVPs, and where it's red, some sort of waveform deformation has been observed, to some sort of evidence that there is a ULVZ, and where it's blue, it's not been observed. But you can see that only a fraction of the core mantle boundary has been targeted. And the seismic waves that are used in these different studies are quite different. Some have energy that reflect off the core mantle boundary. Some have energy that has transversed through the core. So quite a bit of variety of seismic probes, and they all have kind of different disadvantages and advantages, and also tend to see slightly different structures, which could partially be that these ultra low velocity zones show a big variety of the type of structures. But it also could be that our seismic probes just observe them slightly differently. So in some of these cases, there's just a waveform that is quite anomalous that shows some evidence. And that are these cases where there's like one little red line in a certain direction of evidence. And there are only very few places in the type of probes that can kind of find the 3D geometry of these anomalies. And I'm going to highlight these studies now, because so far 3 of them have been mapped and published, and those 3 happen to be based beneath Iceland and near Hawaii and Samoa. And so these are 3 major hotspots, locations where we expect to have a mantle plume. And so on the left here is this really speculative cartoon that these ultra low velocity zones are some sort of base or route to the mantle upwellings that feed into these hotspots. And I'll be saying more about this in this talk. But first, I will like to introduce you to the types of data that my team is mainly using to target the core mantle boundary. And these are called shear diffracted waves. So these shear waves, or S waves, we call them, are transverse waves in the planet. And because the outer core is a fluid, it cannot sustain these shear waves. And so this energy, most of this energy is reflecting off the core mantle boundary, or at the right angle, it will refract onto the core mantle boundary and propagate along it and send energy upwards. And that is our shear diffracted wave. And so we can observe these diffracted waves at large distances from the earthquake itself. And they have some nice properties. So the higher the frequency we can push our observations to, the more it's sensitive closer to the core mantle boundary. A downside, though, is that they have quite a long path along the core mantle boundary. And so any anomaly we see could have been picked up anywhere along that path. And so we get a bit of a poor lateral resolution onto where the anomaly is. So on the next slide, I'll start showing you actually wiggles and waveforms, evidence of what is happening at the core mantle boundary. I'll never really be showing the amplitudes of these waves, but you have to think of them on being of an order of micrometers or even fractions of micrometers of anomalies that we observe here. Okay, so here's a first earthquake that I will be showing you, and I'll spend a little bit of time on this slide explaining the geometry of how we plot this sort of data. This is an earthquake in the New Ireland region in 2010, and it's recorded across a whole host of seismic stations, mainly in the United States. And these purplish dots are showing where these waves start to be sensitive to the core mantle boundary and where they start to come up towards the stations. And so these purple lines are showing the region of where these waves are sensitive to the core mantle boundary. And in the background here is one of these tomographic models I showed. So the slow velocities here are the LLSVPs. That is the main Pacific LLSVP, and they're surrounded by faster blue velocities. These are the type of waves that we would predict for this particular earthquake. So this plot actually has a couple hundred of waveforms in it for all these stations here, but the waveforms are kind of shifted onto their arrival times and then plotted in little groups. So they have a lot of them on top of each other. And the y-axis here is azimuth, which is angle between north and the direction from the earthquake to the station. So as we go from lower to higher azimuth, kind of sweeping across the Pacific here from north to south, seeing different structures. And what you can see in these waveforms is some predicted amplitude variations, and this is due to what we know about this earthquake source that we've put into these predictions. We can also see there's a slight travel move out from these lower azimuths to the higher azimuths, and that is the predicted delay from going from outside the LLSVP to propagating inside the LLSVP. So we've put this background model into these waveform predictions. However, when we look at the actual observations data, it is very, very different, and there's much more variations. So in the observed data, as we go from lower to higher azimuths, so from north to south across the Pacific, you can actually see that this main shear diffracted energy almost disappears towards the higher azimuths. And then 30 to 40 seconds later, we see this delayed phase that has a move out in time here. And this delayed phase is what I'll be calling a post-cursor, or an S-diffracted post-cursor. And so this really puzzled us for a while, what sort of extreme structure can cause these very, very strong delays. And we found that we could approximate these waveforms by putting in kind of a cylindrical, very strong anomaly at the base of the core mantle boundary. This is an anomaly that is about 900 kilometers across and 20% reduced in velocity. We've put it in the black circle over here. And on the right, you can see the synthetic waveforms for this that predicts a lot of this post-cursor and the hyperbolic move out. You can see we model some of the components. We don't model everything. So you can see that like the amplitude reduction in the main phase is a bit underpredicted in this sort of synthetic model. So this is computationally quite expensive to run these full waveform simulations. So this is why we work with these simplified cylindrical models, so we can constrain some of the parameters of this anomaly, the location and width and the velocity reduction. But we cannot constrain, we cannot constrain any anomalous waveform because it's just too much of a parameter search to go through. Okay, so how are we really interpreting this post-cursor energy? So the strong velocity reduction is kind of causing this lens-like a focusing effect of the energy that gets trapped within it, and it scatters that energy across the US. Here's a movie of what of the wavefront prediction. So here the wavefront is propagating down to the core mantle boundary. It then interacts with this ULVZ anomaly, setting up this post cursor or triplications. And then eventually it propagates up to the surface again and gets recorded at these seismic stations with a massive delay time. And so the height is another component. And so we get these height of the anomalies by actually looking into the kind of frequency sensitivity of these post cursors. And so my filters are actually depicted in period here, so 1 over the frequency. What I showed so far was periods between 10 and 20 seconds when we see a very strong post cursor, and also this reduction in amplitude. As we allow longer periods in up to 30 seconds, we actually see a much more arrival of the main arrival coming in. So this is probably energy that's kind of propagating over the anomaly. But at very much longer periods, we don't actually see much of this post cursor energy or any effect of this ULVZ. And so this really means that it's only the higher frequency waves that are getting trapped by this anomaly and are being refracted. And we kind of followed here a rule of thumb for waves that reverberate in slow sediment layers at the surface and get trapped within them, which says the rough height of that sediment layer is related to the period that gets trapped, the seismic shear velocity divided by 4. If we do this rough calculation at the core mantle boundary, we get an estimate of 26 kilometers for the height of this layer. And so we did some more modeling with that and came at a best estimate at 20 kilometer across, but of course there could be variations and morphology on that layer that we aren't capturing by this. And of course the error bar is quite big. So looking 3,000 kilometers deep, we can roughly model that this is the height of Olympus Mons on Mars, the highest anomaly on Mars, plus or minus our highest mountain on Earth, the Mount Everest. So that's the kind of resolution that we get looking at this from this distance. So while there are some uncertainties there, what we can say though is that the aspect ratio is very broad versus very thin. Like we have this anomaly that needs to be around 900 kilometers wide and is only 20 kilometers thin. And so dynamically that indicates to us that this is really ponding of material, and whatever this material is, it needs to be very dense compared to the surrounding material. So this research is really possible due to these large-scale seismic experiments, and this particular one is the transportable array. So the transportable array was this broad-scale experiment that kind of hopped across the US over 10 years. And then after that, over the past 10 years, it has moved to Alaska. And of course, a lot of this gets done to understand the near subsurface and the seismicity and the tectonics of this region. So we really benefit, our research really sort of piggyback science on these amazing and large efforts to put these stations out and install them for Alaska in quite remote locations. So it's a big thanks to the people who do that, and the big efforts in the field to share all of this data as open accessible. A lot of this data come from the IRIS Data Management Center, which hosts a lot of this seismic data. And so I can go in and I can pick the kind of geometries and the bits of the seismogram that I'm interested in and download those, and so can everyone else. So that's really great. Also, the existence of this array in Alaska really allows us new geometries to look at the core mantle boundary beneath the Pacific. And so one new geometry is that there's now from earthquakes just north of New Zealand towards Alaska, we can really look at this Hawaiian ULVZ from a new direction. So this data is a bit less dense and noisier than the one before. But again, we have a bit of a post cursor moving out here. And we found to fit this data that we actually had to move the location from this gray circle to the black circle here, so a bit further away from Hawaii. But we get a much better sense of this location now that we have data actually coming from two directions, because just looking at it from the one direction, we have some uncertainty within that direction of the wave propagation. Also, this allowed us to look at a very different geometry. So this is from an earthquake in Chile recorded across these stations in Alaska. And again, between these dots here is showing the area in the Eastern Pacific that these waves are sensing the core mantle boundary. On the right here, you can again see kind of the synthetic predictions for the waves. So these are again plotted as a function of azimuth. So now from lower to higher azimuth, kind of scanning from the west to the east here across this bit of the Pacific. And then on the right here are the observations. And so one thing we can see in the observations is actually that the initial arrival time of these waves are going from very delayed at the lower azimuth for the waves that have propagated in the west to much earlier arrivals for the higher azimuths or the ones that have propagated in the east. And so this is really due to this boundary of the LLSVP here that the waves are capturing and seeing here. But also there's a post cursor going through this data. A little bit more complex than my previous examples because there's interference here between the main waveform and the post cursor. Part of that complexity is that this earthquake is very shallow and produces some more complex waveform than my previous earthquake that I showed that is a very deep event. One thing we can do with this sort of data on these seismic arrays is actually map the direction of the energy that the energy is coming from in little subsets of stations. And what we do here is that we assume a plane wave coming across a subset of stations. We can assume a certain direction, estimate the travel time delays that we would expect between the different stations, and we can stack the energy together from this particular direction. And we can do this for all sorts of trial directions. We can see from what direction the arrival of the energy is most coherent. And this is an example of that sort of stack. So in the x-axis is time, and on the y-axis is back azimuth. This yellow dotted line is where we would expect energy from the earthquake to arrive. And so we can see a big blob of energy arriving roughly from the direction of the earthquake. And then at a later time, but from a very different direction, we can see this post-cursor energy. So we can do this exercise for a lot of different subsets of stations that we have there. And here you can see a back projection of where the energy comes from. The blue is the main energy, the main blob. And this, what I labeled SDiff plus, is the post-cursor energy. And so the post-cursor energy is consistently coming from somewhere within the Pacific. And so we can interpret this to be a ULVZ. It's similar to the case in Hawaii. And so here's a movie of the wavefront. And so the waves here that are coming from the western boundary of the ULVZ here will arrive at the stations here, coming from a different angle than the kind of direct energy that went around this particular ULVZ, causing this change in direction. And so we've mapped this ULVZ again with similar parameters of the Y, a little bit smaller this time, 600 kilometer in width and 25% slow. And the location of the ULVZ is kind of to the west of the Galapagos here. And this, on the right here, you can see the synthetic waveform predictions for this particular event. And so we can kind of get the delay time and the move out for this particular post-cursor, looking a lot more like the data than the reference synthetics do. And here are the waveform predictions that we would have for this model. Here's a different event, Chilean event. It's roughly the same geometry. And you can see in our observations, this one actually has a very, very weak post-cursor going through. And the cause of the weak post-cursor here is actually just due to the source type of the event, which is sending very little shear wave energy in the direction of the ULVZ towards the western boundary of the ULVZ here. And so you can see that in our synthetic model, this prediction that for this event, the post-cursor is much, much weaker is kind of reproduced in our synthetic model. So I'm showing you here the results for a best fitting model, but actually just with these two earthquakes that are viewing or sampling the ULVZ in this one single direction, we actually have very bad resolution on where this UVZ is. We could locate it here, but we could also locate it much further north, maybe change the size and velocity reduction a bit, and still get a really good fit to these waveforms. And so the big hunt was actually to find some geometry where the waves crossed through. And so my PhD student actually did this massive search for all the potential earthquakes that could be sampling this region. And we found tens of earthquakes that have some evidence for a post-cursor in it. They're all not all great quality or very, very clear. They can be very, very noisy. And so besides these two, we added two other events to the clear modeling. And this one event, so this is happening, this is an earthquake on the ridge towards Antarctica, and it's sampled across a lot of the US. And it's sampling the ULVZ from a very, very different direction. And again, we see some sort of post-cursor coming through here. It's a bit more difficult to track across all the azimuth. You can see in our synthetics, we kind of predict that the post-cursor should be here everywhere, or the amplitudes of our post-cursors are a bit higher than they are in the data here. So there's some suggestion here that maybe our ULVZ shouldn't be this perfect cylindrical shape that we're using here, but this is just a limitation of this method, which I sometimes call trial and error forward modeling. And here's a final event, just because this event shows a bit of a different angle again. And really only the earthquakes between this event in Fiji towards the Caribbean should see the ULVZ here. And we can see that there's a scatter of waveforms here. The seismic station distribution is just not as dense here to be able to kind of track your eye where the post-cursors are going here. You can see there's maybe some reproduction in the synthetic model here, but it's really hard to fit this. Partially, though, I want to show this event because it has really good coverage towards the US. And this is just an example of a region where we don't see a post-cursor, where the observations fit our synthetic predictions quite well without putting any anomaly in. And so this is really showing us that it's not the whole core mantle boundary that is covered in these anomalies. They do seem to be quite localized, and there's a wide region of the Pacific here where we don't see a big anomaly like that. So now, is this anomaly connected to the Galapagos? So here I'm showing a couple of these tomographic models again, but now in a kind of vertical cross section, and we're going across here, across the area of our ULVZ and towards the Galapagos. And so our ULVZ here at the base, based in these low velocity anomalies at the base of these models. And then one can speculate, you can see there's quite some variation in these models. Is there a connection from here in a full upwelling towards the Galapagos? Of course, some of that upwelling could happen out of plane with this. But for there to be a connection, there also has to be a shift of a couple hundred kilometers towards the east of the plume, going from the base to the top of the mantle. So here's, this is a map of the previous compilation of ULVZ and ULVZ studies. I'm just highlighting on there the 4 now that have been mapped in 3D, of course, with the limitation that some of these are just these simplified cylindrical models. And those are Iceland, Hawaii, Samoa, and Galapagos. And so, I'll make some a speculation about the connection between these and the hotspots. And I say there's speculation because we only have 4 samples of this now, right, to make this kind of correlation between the core mantle boundary and these hotspots, and more work would have to be done. But for one thing, we can look at estimates of the plume buoyancy, or the kind of heat flux of these mantle plumes at our surface. We kind of see that due to the upwelling of our surface. And these are estimates for all the different hotspots around the planet. And you can see that Iceland, Galapagos, Hawaii, and Samoa all are pretty major mantle plumes with a big heat flux. There are also geochemical signatures in the ocean island basalts itself that we can look at. And the first I'll introduce to you are these helium-3, helium-4 ratios in these basalts. So helium is very easily degassed over time. So any rock material that comes in contact with the atmosphere would easily lose its helium content. And so as our mantle material kind of cycles through the plate tectonics, I think over geological time, a lot of the mantle has been degassed. And we can kind of see that reference helium signature at mid-ocean ridges. This is where mantle material comes up and forms new plates. But it's different from our ocean island basalts or hotspots, where we think the material that is coming up are these hot upwellings that are coming up all the way from the core. And so we also see a different helium signature there. We see it's much more enriched in helium than at our reference location. And so it seems to tap from some sort of deep reservoir that is undegassed. And that could be a material that has been dense and sitting stably on the core mantle boundary over geological times, or potentially it has been recently introduced that our core could actually be hosting a lot of this helium. And so it could be a signature of some helium leaking from the core in these particular plume locations. This is a compilation of the helium signature across all the hotspots on the planet, on the map form on the left here, but organized by the strongest anomaly found in these locations for these different hotspots. And here, the gray line here is the mid-ocean ridge basalt reference. And you see here the four that pop out the most are Iceland, Hawaii, Samoa, and Galapagos, happening to be the four where we've now identified these kind of big mega ULVZs at the base of the core mantle boundary. A different signature are these tungsten isotope ratios. So this is 182 tungsten over 184 tungsten. The 184 tungsten is very stable isotope, but it likes to sit in an iron-rich environment, either iron-rich reservoir at the base of the mantle or preferably within the core. So we think in the formation of Earth's core and mantle, a lot of this 184 tungsten went into our core. 182 tungsten, though, is a decay product of the lithophile hafnium. It has a very short decay time, though. So while the hafnium went into the silicate mantle, and it was enriched in hafnium and then decayed into 182 tungsten. So we expected much more 182 tungsten within the mantle. And again, we can look here at the difference between the mid-ocean ridge basalt and the ocean island basalts. So if we take our mid-ocean ridge basalts as the zero reference case, then we can look at the parts per million difference that is observed in ocean island basalts. And we get this slightly negative signature. So there is less 182 tungsten over and more 184 tungsten in these locations. And some of that could be a signature of the very strongly different prediction for this ratio within the outer core. So this is again a compilation of all these of very recent studies that have been sampling this across a lot of the core mantle boundary. In the gray bar here is the kind of reference for the mid-ocean ridge. And again, we see these quite negative samples pop up for Iceland, Hawaii, and Samoa. The study on the right added a lot more other hotspots. And here in orange, you can see Galapagos pop out as a very anomalous one. So I've compiled this all here on a map. The blue triangles are scaled by the strongest helium anomaly, and the green triangles are scaled by the strongest tungsten anomaly. And so, yeah, a lot of these big anomalies are now close to these locations of mega ULVZs. But obviously, it would be great to target a lot more of the core mantle boundary. So I'm going to highlight a couple other research directions that we are taking with these types of waves. One thing we want to do, kind of push this to higher frequencies or shorter wave periods to kind of sample that finer structure close to the core mantle boundary. And this is work by T. Lee, who has just finished his PhD here. And this is, again, looking at the Hawaii event that I first introduced. The top is the 10 to 20 second period band that I also showed before with the post cursor. And at the bottom here is pushing it to 3 to 6 seconds. Data, there's a lot less energy there. There's also much more seismic noise here. Yeah, I hope to convince you that there's already some consistent energy coming through here at a much more delayed time. And so again, with this energy, we can look at the directionality of this energy through our beamforming stacks. So here are some examples of that. On the left are 2 examples at the longer periods or the lower frequencies. We can see our main blob, and we can see our post-cursor blob, which is coming a bit more from the south. So it's coming from the southern boundary of the UVZ here. And then we can do the same for the high frequency. And we can see that the delayed post-cursors here are coming from quite comparable back azimuths, but they are much, much more delayed in time. We can clean up our waveforms a bit by kind of stacking them in little groups, but stacking them assuming the direction that we have observed. So we stack the main phase and the post-cursor separately. And this really highlights this kind of high frequency delayed energy that is happening here. And so we can see that the waves that are sensitive closer to the core mantle boundary are trapped in some sort of even slower velocities and get refracted even more. And so we did a lot of modeling on this. Of course, we cannot fully uniquely model this sort of layering, but we can say that there has to be some sort of quite strong layering in the internal structure of this ULVZ. And this could be fit by like a bottom layer that's a couple kilometers thick and 40% reduced compared to the general 20% reduction in the rest of the ULVZ. My PhD student, Carl Martin, is trying to push us to a more global approach to be able to say a lot more about where these are in total. And so he's been in a massive effort collected all the shear diffractive waveforms that are possible, also really pushing down on the magnitude of the earthquakes that he was looking at, finding over 7 million core diffractive waveforms and go through them by eye. And of course, you need to have a good geometry and good waveforms, good station coverage to identify these post-cursors. So he's identified post-cursors in about 0.3% of this data set. And in other cases, he can also more confidently say that there's not a post-cursor. And these are preliminary results on this. And so on the left, you can see, regions that have been mapped so far, but also we are targeting new areas where we have evidence for an ultra low velocity zone. And on the right, you can see there's large parts of the core mantle boundary where we don't think there's evidence for these ultra low velocity zones. I should say that other seismic probes have seen sorts of structures here. And so that could be partly due that our diffractive waves are really only sensitive to these very broad scale kind of mega ULVZs. And if they're smaller scale ridges or something, then we don't produce these post-cursors and we don't really see this. So this is where seismic probes could differ on what they see on the core mantle boundary. Just in his database, there is a catalog of over, around 70 earthquakes and over 10,000 waveforms that just sample the Hawaiian ULVZ alone. And so we're somewhat in for a challenge how to use this data because this is a big data set to kind of produce these full waveform synthetics for all the potential different models. And so we've been moving towards using this more simplified forward model with our waveform prediction to just predict the travel time delay of the post-cursors that we're seeing, and using those travel time delay observations, kind of explore the space of ULVZ space of ULVZs that is observing this. And this allows us to include a lot more seismic events. And so we are applying a Bayesian inversion here, where we can go through lots of different models and find a family of models that successfully fits our data. And here are some preliminary results. There's still a bit of a simplified parameterization with just one sort of allowing for an elliptical model that can change shape and location and velocity reduction. And on the left here, so the red here is showing the median of the ensemble of models that have fit our initial data, compared to the black dashed line, which was our previous UVZ suggestion. And so it's actually suggesting that this anomaly is smaller, but more reduced in velocity, and is actually elliptical in shape. And on the right here is showing the standard deviation across the suite of models. And it shows this very, very dark ring, which is what is to be expected, and great to see. And this is kind of showing the trade-off that we can fit the same data with a slightly bigger anomaly, but less reduced in velocity, versus a smaller anomaly that is more reduced in velocity. Additionally, we've been working in this multidisciplinary effort, and this is with geodynamicist Julian Dunberg and Renee Gassmuller and mineral physicist Robert Myhill. And this is a really multidisciplinary effort to understand if these UVZs can be partially molten. We put a melting model into this. We have to make some assumptions to actually cause the material to melt here. But this geodynamical model also allows the solid and the fluid to move on different timescales. And so we can predict kind of behaviors here that we expect. And we don't really reproduce these broad anomalies that we see seismically. So we might have to introduce some initial compositional components of ponds in this first to actually reproduce the seismic velocity anomalies. But we also see that if we have any sort of melting model, the iron really likes to go into the melt, and it produces this dense thin layer at the core mantle boundary. And so we were also questioning out of this if they're UVZs are kind of a local phenomena, and if they're sitting in this kind of globally anomalous melt layer at the core mantle boundary, and can seismologists actually observe this? So with the shear waves that I showed so far, we cannot observe these melt anomalies because the shear waves just observe it as a liquid and wouldn't see the difference between the silicon melt and the outer core. And so we really have to look at compressional anomaly waves for this, and also look at them at very high frequencies to be able to target these very thin layers. And so we tested many different potential probes of compressional waves that interact with the core mantle boundary to find the one that would be most sensitive to this. And we found these quite rather exotic waves. So this is one wave that travels through the core and bounces off the core mantle boundary, gets picked up by a station here. And in the same seismogram, we can see a wave that has diffracted parts along the core mantle boundary and arrives at this station a bit later. And actually looking at the travel time difference between these two waves gives really a good sensitivity to the average core mantle boundary structure that this wave observes. And so Stuart Russell has been doing this work, and he's been collecting this global database of these differential travel times. And on the right here, you can see a histogram of his global data results. And there's actually quite a spread in this. And you could actually hide a signature of a global melt layer, maybe with some variation in thickness easily within this spread. So that is sadly a bit disappointing that seismologists probably cannot say that the core mantle boundary is fully sharp, or maybe there's a fuzzy boundary. And that has a big influence on how the core and the mantle can interact with each other, both in heat flux and in material transport. In this database, there's some interesting geographical variations that we are currently looking into a bit more. So in conclusion, I've introduced you to these dense kind of mega UVZs that currently have been mapped near Hawaii, Iceland, Samoa, and Galapagos. So we're suggesting that they are the potential base to the mantle plumes that have formed these volcanic islands here, and potentially linked to the isotopic signatures that we see at the islands, inferring that these anomalies must be primordial over Earth's time, or actually containing a component of leaking out of the outer core. I've shown you some other directions we're taking this, pushing to higher frequency to actually zoom in a bit more into the core mantle boundary and seeing the internal layering within this UVZ, and also targeting potential melt layers on the core mantle boundary. And I've shown you a bit about how we're expanding these techniques to be able to use much bigger data sets and moving away from this imaging of a single earthquake at a time through the waveforms. Just as a quick highlight, we have my team has been building this museum exhibit at the Sedgwick Museum of Earth Sciences in Cambridge. So if you're in Cambridge or maybe near Cambridge or have some free time once you're there, I suggest visiting the museum, and our exhibit is called The Deep Earth Explorers and gives more background and has some interactives about how we use our data. I'm happy to take any questions on my talk.
Sane, thank you very much indeed for that. That was absolutely fascinating. Belinda should have been following the questions coming into the chat. And I also see that there's another little button called Q&A. So there seem to be 14 comments in the chat and 2 in the Q&A, but I'm going to hand over to Belinda to sort out exactly what's what and to put the questions to you. Thank you again.
Okay, thanks, Steve. Yes, thanks, San. That was fascinating, particularly for an astrophysicist like myself.
Looking down instead of up.
Fascinating how you do these observations. So there's one question in the Q&A, which I'll do first because that should cut that off, and then I'll go back to the chat. It's from someone called AC and says, could the LVZs be the non-mixed remains of THEIA? And I don't know what that is, but maybe you do.
Quick look.
Yeah.
I'm not entirely sure what is referred. It might be an impact. Might be idea. So there's some ideas that the material that sits around here is a leftover from a meteorite impact, or the core of a meteorite impact that has leftover material at the top of the outer core in the OVZs, which is, yeah, I guess another potential anomaly. Yeah, I'm not sure if we can. Yeah. Could have, I guess, also similar isotopic signatures that could be being entrained in the mantle plumes here. I hope I interpreted that question correctly.
Me too. Okay. In the chat, there are several questions from Jeffrey Greenspan. I'll take the first, and then see if there are some other questioners before going further down. So his first question is, what are relative rates of reactions between the mantle and outer core versus the rate of upward migration through the mantle? Do differences in these rates influence properties such as magnetic field or seismic activity?
So in the heat flux rate, it definitely, any lateral variations has an influence on the magnetic field and the magnetic field generations. In terms of material flux, it's actually, it is quite unknown and is quite debated. It's even debated in what direction material is fluxing, or is iron going from the mantle to the core the other way. I think you can make it go both ways, as far as I understand this field. As well as if that reaction happens, if you can entrain it away from the core mantle boundary, or if you just end up with kind of a thin layer of rust and that remains stable over time. And so people have been looking at morphological instabilities to kind of cause this flux of material, or cause outer core material to be get trapped within the mantle. But there's a lot of uncertainty on this, and uncertainty within the flux. And so it's really still speculating what fraction of this it's coming from the core, and if it can be entrained from the OVZs in these mantle plumes. This whole dynamical picture is not fully constrained yet.
Okay, thank you. There's a question from Jack Mueller, who says, hi, thanks for the great talk. About the potential for a fuzzy CMB, could I ask what the implications for reflection/transmission coefficients of CMB interacting phases would be?
Yes, it would be a variable, and we did look into this, but then so the SCS waves, the S waves wouldn't really be sensitive to it because it would just observe a liquid, but PCP would. So these are the longitudinal waves that reflect off the core. They are very, very tricky waves though, because they are quite small in amplitude. And yeah, what we've found so far in studies is that the amplitudes massively vary. And so I think you can easily hide a fuzzy boundary within this. The other thing that I've kind of glossed over is that obviously can also be topography on these boundaries, which also affects the amplitudes. Yeah, and yeah, the observations are so varied that you can hide all sorts of these studies in here. This is why we were really trying to find a probe that had travel times, which was a bit more robust than looking at amplitudes. But the predictions would surely change with a fuzzy boundary for the longitudinal waves.
Great, thanks. Another one from, I'm not sure I can say this name correctly, Coyote Agbula. Says, thanks for the lecture. Aside the high resolution of diffracted S waves, are there any other reasons for this choice of seismic phase over other seismic phases such as SCS, SCP, PCP, etc.?
Yeah, so these are waves that have reflected off the boundaries, and they do get used to look at UVZs, and we have used them as well. So if you use these waves, they cause little reflections off the top of the UVZ and ones that have bounced inside and have gone up. But the vertical travel times in these UVZs is quite minor. So when you use these phases, they're only a couple seconds apart. So you have to go to quite high frequencies to differentiate these pre and post cursors in these phases. And actually they're quite weak in amplitude as well. So when you use these phases, you typically have to stack multiple seismograms together to see it. So I actually think an advantage of the shear diffractive waves is that we can see these in the raw data. That is quite unique for seismic. We don't have to do any data stacking to bring it out. You can see these anomalies, and they are delayed by 30 or 40 seconds. So much more than a couple seconds that you would get for vertically propagating waves. But then again, the vertical ones would have a very different resolution and different trade-offs. So ideally, we could combine these two phases in some way. And we have looked at SES waves on Hawaii and seen that they do have evidence for much more morphology in these UVZs than these diffractive waves can see, because they kind of just average over the full structure. And so I think the combination of these will surely be needed to really understand these ultra low velocity zones.
Thanks. Okay, another one from Jeff Greenspan. Is the upper part of Earth's outer core dissolving the lower part of Earth's mantle?
Yeah, this is one potential, yeah. So if these are iron enriched, there's a thought that actually the iron cannot go in, the iron cannot remain there, but will go into the outer core. Yeah, or is it the other way? So that is really an unknown and is a difficult question in thinking that there might be a dense primordial layer at the base. Yeah, is a problem for mineral physicists.
Okay. There's one from AC. Are magnetic field anomalies such as the South Atlantic anomaly correlated with any of these features?
So I don't think there's a direct correlation, but yeah, there are attempts to kind of understand what the kind of heat flux variations are from having these kind of piles of anomalies, and also having cold slabs hit the core mantle boundary where there can be a higher heat flux, and what effect that has on the overall convection patterns in the mantle and what the magnetic field would observe. But there is a general problem that computationally we cannot fully model how vigorous that convection is. It's just too big of a computational problem. And so there are these open questions about how it behaves, also how our magnetic field flips around, and if this is also correlate with how heat flux variations are in the core mantle boundary. So while we see enough evidence that there is a connection between these two, it's not fully understood, but I know there is some research that trying to explain the South Atlantic anomaly due to what is happening on the mantle side.
Okay, I'll go down to Jeff Greenspan's next one. How do characteristics of the Earth's core mantle boundary affect reversals of Earth's magnetic field?
Yeah, so that is related to that, yeah, to potentially these heat flux variations. And there has been some research showing that there's a correlation with times when more slabs are arriving at the core mantle boundary, potentially causing an increase in reversal. Yeah, but fully understanding the reversals and the relationship with this, I think, as far as I'm aware, but somebody can maybe feel like this is not fully understood. Yeah, these are.
So Belinda, I'm having to keep an eye on the time for this meeting. I wonder, I think Sunny's answered a lot of questions already, but I wonder if you could pick out just one final question for Sunny before we say thanks very much again and let her go and get a drink or something.
Okay, so the second one from Coyote Agbula is, what is the origin of the mega ULBZs in your study? Is thermal or compositional anomaly, or probably a combination of both?
Well, I don't think it can just be thermal. The seismic velocities are just too extreme that you cannot explain it with temperature that the outer core would have. So it has to have some compositional component. So an iron being a prime candidate for that, as well as that the boundaries are quite sharp to cause these waves to be trapped. And so that has to be some sort of compositional boundary and can't be a fuzzy thermal boundary. But once it's compositional, it has to be a combination of both, since this anomaly sits on the core, so it will heat up. So it will also be quite hot. So some of that velocity reduction is the heat, and some of it is the compositional anomaly. Yeah,
Okay.
thank you all for the questions.
Yeah, thank you for your amazing answers to all of them. And for a wonderful talk. Several people also sent messages saying what a lovely talk it was. So
Indeed, indeed, absolutely fascinating talk, and thank you very much indeed again, Sunny. I just want to, in closing the meeting, remind everybody that the AGM is on Friday the 13th of May at 4 p.m. and that voting for the RAS Council is now open, and you do that in the members section of the RAS website. And then finally, I give notice that the next monthly ANG open meeting of the Society will be on Friday the 7th of October. Seems an awfully long way off, and maybe we can all actually physically get together by then. But thank you all very much indeed for coming along and for your attention. And thanks again to Sunny for an absolutely fascinating talk. I declare the closed.
thanks, that was wonderful.